Okay.
What's the PDF?
Yeah. I mean, what I would do is I will just keep the problem, then I will go through the yeah. So you can take them off. Yeah.
This is really hard. It's 1 over.
There is an attendance sheet coming around. Make sure that you sign your name. Only your name, not nobody else's, okay? Just sign only your name.
In a moment. Oh, it's not there. Yeah, it's the expectation of each. That's what I was thinking. Yeah, each would take us. Yeah.
You guys have to. Yeah, that's good.
Looks like an act. Alright, so can you try question 1, sir? Yeah.
It's dx, by the way. It just goes to a function of t. That's why it's got t in it.
Right. Can you see me writing, guys? Yeah. Okay. So I see that many of you have already done question 1, and some of you have already done all of the questions. I guess this is too easy. So let me show you. I mean, those of you who haven't done this question, let me show you how to do this. Okay. Now the MGF of a normal variable is just, by definition, is the expectation of ETX. So it's the integral of ETX multiplied by the PDF. This is the PDF of the normal distribution, right? So this will become okay. Yes. And then in the next step, I'm gonna take this as a common factor. That is 2 sigma squared as the common factor. So this will become right. You see what I've done? I've taken this as the common factor, so the numerator becomes this. Yeah. In the next step, I'm gonna take a minus sign out of this, right? So if I take a minus sign in front and open the brackets around x minus mu, you will get the following. You get minus do you guys see what I've done? I've taken a minus sign outside. So what you have here is just comes from this, right? And also I have expanded x minus mu squared. That gives you 3 terms, right? That gives you 3 terms. Now the next step, what I'm going to do is I'm going to combine the two x terms. You see, there are two x terms, this one and this one. So this will become x squared minus 2 mu plus sigma squared t x plus mu squared divided by 2 sigma squared dx. You see what I've done? I have combined. This is one of the terms that has an x in it. This is another term that has an x in it. I have combined these two terms to get this one. Yeah. Right. In the next step, I'm going to do something that should be familiar to you. Now, what have I done here? And you tell me what I have done. From this to this, this is known as the you heard about this term, completion of squares. I'm sure most of you. No? Yes? Or no? You guys heard about the term completion of squares? Yes. So what I have done is to rewrite this in this form, and this process, the process of writing this in this form, is known as the completion of squares. Right? Okay. Now I'm going to do the following. I'm going to I have rewritten this in this form. Now let me ask you, the thing I have highlighted in this box, what can you say about that, guys? This, the thing inside the box is what? Must be equal to 1. Why? This must be equal to 1 because alright, can you see this, guys? It must be equal to 1 because what you are integrating is the PDF of a normal distribution with parameters mu plus sigma squared t and sigma squared. And any I'm sure you learned this in probability 1, that any PDF must integrate to 1. That's not just the normal, but any PDF must integrate to 1. And therefore, the thing inside the box must be equal to 1. Yes? Yes, all right, sir? Yeah. Maybe it's too simple for you guys. But I mean, all right, so the answer is equal to this. Because this is 1, this is the answer. And this answer simplifies to this one here. You should take a couple of minutes and see that this will simplify to mu t plus sigma squared t squared divided by 2. So that completes question 1. All right. Any questions about this? I'm sure maybe it's too simple for some of you. Yeah, I guess. Can you do the next question, guys? Question 2, please, now. If that is okay, can you do question 2, please? Are you okay? Can you make sure that you sign your name, guys? Anybody who hasn't signed this? Yeah, to come please. Just. Do you have a question? Okay, it will come to you in a minute. Yeah. You guys do question 2, please. I'll give you a few minutes and see if you can do it. You guys want to sign?
No.
All right, guys. Let me show you how to do question 2. Right. I know some of you have already done it, so please don't complain about being bored. But so you have two variables, x1 and these are independent random variables, right? Independent and normal variables. Okay. The question is to show that we want to show that ax1 plus bx2 plus c right, we want to show that this linear combination, this is a linear combination of x1 and x2, is also a normal variable with these parameters. Now to do questions like this, well, there are many ways you can do this, but one standard approach is the following. What you do is, right, let me call this, just for the sake of notation, right, let me call this y, right? And I will begin by finding the MGF. I will begin by finding the MGF of y. All right, that's the first step, is to find the MGF of y, right? Right, which is by definition is the expectation of E of ty, and this is the expectation of E and this you can write as the expectation of E T A x1, expectation of T B x2, E T C. Right. Now the next step, I'm going to use independence, because we are told that x1 and x2 are independent random variables, right? Because of that, we can write this as the product of expectations. This is a constant. This term is a constant, right? Are you guys with me? Because x1 and x2 are independent variables, we can write the expectation of the product as the product of the expectations. That's the property of independence, right? Now, this guy here is the MGF of x1 at TA. This guy here is the MGF of x2 at TB, and this is simply this, right? Now we know from question 1, this is the formula for the MGF of a normal variable, and we know that x1 is a normal variable, and therefore by this formula, this guy here is mu1 TA plus by this formula. And once again, by this formula, this guy here you can write as mu2 TB and finally this term here, E of t c. Are you guys with me? All right? Yeah. So we have now the product of three exponential terms. Remember, when you take the product of exponential terms, you are basically summing the powers, right? So this is equal to all right, this is equal to this because of what I just said, that when the product of exponential terms is the same as an exponential term with the power being the sum of the individual powers, and that's what I have done here. Okay. Now if you compare this with, now let's compare this formula here with this formula here. What do you see, guys? In place of mu, we have this expression. In place of sigma squared, we have this expression. And therefore, by comparison with this is the MGF of a normal variable with parameters. This being the mu parameter, and this being the sigma parameter, sigma squared parameter rather. So what we have shown, let's go back. What we have shown is that by taking the MGF of this, we have shown that it is equal to something. It's equal to something that is the MGF of a normal variable, and therefore we have established that y, the variable y. Remember, I denoted this by the variable y. The variable y is normally distributed with the parameters mu1a, mu2 plus mu2b plus c. That's the first parameter. The second parameter is this. Is that clear, guys, or not? So, you're right, guys. You don't follow? Huh? Are you guys okay with that? Yeah. See, the approach is some of you seem kind of lost. I don't know why. But some of you seem too simple for this. Yeah. I mean, you see the approach I have taken to show that this follows this. You start with the left-hand side. Call it whatever you want. You don't need to call it y. You can call it z or w or omega or whatever, right? And find the MGF of the left-hand side, which is what I'm doing here. Trying to find the MGF of the left-hand side, right? And simplify it as much as you can, and until you come to this stage here. This is the simplest form that you can simplify to, right? Now, what you have here is, by comparison to this formula, what you have here is the MGF of a normal variable with these parameters, right? And therefore y must follow this normal distribution. So that's the argument, right? It's simple. Yeah? Or not? We will do more examples like that later on. But can you now do question 3? You should follow this. And you now. You guys do question 3, please. You can assign it as well. You're all set. Any time question 2?
Yeah. So we just
Alright guys, so this question is similar to question 2. So this, you need to follow exactly the same step as I did in question 2 to do this. So I'm going to start with the left hand side, right? Which is x bar. X bar is this average of the x's, right? So I'm going to find the MGF. I'm going to find the MGF of x bar, which is, as you know, is the expectation of t x bar. Yes? And this is the expectation of okay, and this, because of independence, you can write this as yes. Yep. Now each of these guys is, this one is the MGF of x1 at t by n, and this one is the MGF of xn at t by n, right? So basically they are all the same because x1 to xn are IID variables. So this is basically the MGF of x1 at t by n raised to the power n, because all of these terms are the same, right? x1 to xn are IID normal variables. Now we know from question 1 that this guy here, the thing inside the square brackets, is equal to mu times t by n plus sigma squared you see what I've done here? I have replaced this by this, with t replaced by t by n. So wherever there is a t here, I have replaced that t by t by n. Okay. Now taking the power to n, this will become right. You should take the nth power. If you take the nth power of this, you get this. Yeah. Now what you see here, what you see here is the MGF. Now you should compare this with this. The only difference between this and this is that you have sigma squared by n in place of sigma squared. Therefore this must be the MGF of a normal variable with parameters mu and sigma squared by n. And therefore we have shown that x bar is the sample mean, is a normal variable with parameters sigma squared by n. Right? Is that clear, guys, or not? Are you okay with this, guys? Yes? No? Yeah? This does not prove that. Are you okay with that, guys? You're right. You okay with this one? All right. Can you move to the next one, guys? Question 4. Question 4 is trivial. I mean, All right, guys. You know the uniform distribution, which is defined. You know the uniform distribution that has the PDF given by this when x is between a and b. The question here is to find the MGF. I mean, this is pretty trivial, actually. I mean, I know it's embarrassing to ask this question, but anyway. So to find the MGF, you just integrate from a to b of ETX. Okay. So this expectation of ETX times the PDF dx, right? So this becomes taking the limits, you get all right. So that's the answer. All right. So there's nothing to it really. Question 4, right? Pretty trivial. Yeah. And let me also do question 5. Question 5 is an exponential variable with parameter lambda. I'm sure you've seen this in your probability 1 or 2. This one has the PDF equal to lambda e of minus lambda x greater than 0, right? So the MGF will be, you guys okay? The MGF will be E of tx times Now the integral of this is not difficult. You take the lambda outside, write it like what did I do? Lambda I messed it up, sorry. This should be x here, sorry. This should be x lambda minus t. X here. Alright? Now, alright, the integral of this is trivial, is equal to this. Now taking the limits, at infinity the limit will be 0, at 0 it will be this, right? Therefore the answer is lambda by lambda minus t. Alright, so that's the MGF for an exponential random variable. Question 6, I don't have the time to do question 6 right now, but I hope you can do it by yourself, right? If you have questions, feel free to come and see me. I will upload the scanned version of everything I have written later today, so you'll be able to see it online, okay? I will also upload the podcast from this session. You'll be able to see that today later on. Okay?
Why did you say that?
From the minute you left
I guess. I'm not tired. You mean you drink some cold?